Bienvenidos al Laboratorio Internacional de Partículas Elementales de la Universidad de Guanajuato. Lo fundamos el año 2005 para estudiar las partículas elementales y desarrollar tecnología de detección de radiación, incluyendo rayos cósmicos. Hemos atendido a más de 100 estudiantes de servicio social, 30 estudiantes de licenciatura, 20 estudiantes de maestría y 10 estudiantes de doctorado. Desarrollamos investigación en tecnologías de detección de radiación. Hemos logrado algunas innovaciones que han merecido premios nacionales e internacionales. Colaboramos en experimentos internacionales de primer nivel. Hemos creado el seminario Lederman, difundido internacionalmente a través de medios digitales.
Ha llegado a más de 1 millón de personas,
especialmente jóvenes de Latinoamérica, en 6 meses. Contamos con invitados internacionales expertos, líderes en su área y de primera línea, que exploran las fronteras de la ciencia. Hemos publicado más de 22 libros de divulgación y referencia y más de 100 artículos de ciencia en revistas indexadas a nivel internacional. Los esperamos. Bienvenidos.
Let me start this presentation in Spanish. Saludos y agradecimientos desde la Universidad de Guanajuato, en colaboración con el programa STEAM de la Universidad de San Carlos de Guatemala, con la Embajada de los Estados Unidos en Guatemala, con la Cátedra Eugenio Méndez Docurro y la Escuela Superior de Física y Matemáticas del Instituto Politécnico Nacional en México. Gracias a todos ustedes, hemos llegado a casi 1.300.000 participantes desde que iniciamos esta serie de seminarios Lederman. Tenemos en promedio 1.000 participantes por día. Sabemos que nos siguen en ese seminario de casi todas las Américas, desde Argentina, Chile, Perú, Colombia, Uruguay, Guatemala, Salvador, México y otros países de Latinoamérica. También tenemos noticias que nos contactan de España, de Alemania y por supuesto de Estados Unidos y de otros países del mundo, de los países de Asia Central, por ejemplo. Hemos detectado algunos participantes. En este seminario tenemos como invitado al profesor Dennis Marks. El profesor Marks es profesor emérito y jefe del Departamento de Física y Astronomía y Geociencias de la Universidad Estatal de Valdosta en el estado de Georgia, Estados Unidos. Él imparte este seminario titulado Real Qubits, Complex Qtrits, Quaternionic ququads. No lo puse en español porque suena muy parecido en español. Esperamos que sea de mucho provecho para estudiantes de física y para los estudiantes y público en general del mundo. Les recuerdo que recibimos sus preguntas por chat. Now let me say some words in English. Thanks, Professor Dennis, for accepting to speak in this Lederman seminar, and you are very welcome. The public is yours. Thank you.
Thank you very much. And let me start by thanking the organizers, particularly Dr. Segura, and all of those participating in the Leon Lederman seminars. Thank you so much. Let me share my screen with you so I can go directly to my to my talk. And I hope you can see my screen. I'm going to be talking about real qubits, complex Qtrits, quaternionic ququads. And let me just briefly give you an outline of what I'm going to be talking about. I'm going to be using geometric algebra This is a little different from algebraic geometry, and I'll explain the difference between the two. And I'm going to use real geometric algebras rather than complex ones, because real geometric algebras distinguish between space and time. I'll start by talking about the Euclidean plane and the Minkowskian plane, and then generalize to other space-times. And we'll see that geometric algebra is a periodic in metric signature, but recursive in the number of dimensions. And I hope to persuade you that the Heisenberg relations between momentum and position, Bell correlation, and Schrödinger's cat can all be understood geometrically. So this provides a geometric unification of relativity and quantum mechanics, fulfilling Einstein's dream. Einstein used geometry for macroscopic physics, describing time as the fourth dimension in special relativity, and gravitation as a manifestation of the curvature of space-time in general relativity. On the other hand, Heisenberg used matrices for microscopic physics, quantum mechanics, and I'll show you that I hope that by using geometric algebra, which expresses geometry in terms of matrices, we can unify the two. And let me simply remind you back from high school about algebraic geometry. In algebraic geometry, you use algebraic expressions to describe geometric objects. And this is an example of that, where you have the x unit vector and the y unit vector in the Euclidean plane. And then vectors are simply combinations of the two. And the x and y vectors are orthogonal to each other. On the other hand, in geometric algebra, the geometric objects are represented by matrices. So in the Euclidean plane, the position vector is given by this matrix, which can be broken down into a representation of the x unit vector and the y unit vector. And you can show that these matrices have the same relationships that you expect from the unit vectors. So the matrices do what the arrows say. So think of the X matrix is going one step in some direction, the Y matrix is going one step in some other direction, and the geometric algebra is all of the possible combinations of these two actions. You can do nothing, which leaves you exactly where you were, the identity matrix. You can go one step in some direction. You can go one step in some other direction. Or you can go one step in some direction while at the same time going one step in another direction. And that sweeps out the plane that's spanned by those two matrices. And you can show that that area is necessarily time-like. You can use that time-like nature of the bivector to have the vector perpendicular to the bivector, and this only works in 3 dimensions, by the way, to represent that area. And so then you can form the X matrix and the T matrix to form the Euclidean plane. And I like to think of it as the left-hand rule. You've got the X direction and the Y direction, and then the T direction perpendicular to them. So now you have the Minkowskian plane generated by the Euclidean plane. So that's how you get the Euclidean plane and the Minkowskian plane. So two-dimensional, either two spaces or space and time. But what if you've got a different number of dimensions? What then? And mathematicians have worked out what kind of matrices you need to describe different numbers of space and time. It's called the Clifford checkerboard. And I've colored it in so that you can see the different kinds of matrices that you need to describe different numbers of spaces and times. And if you look at this, you see that the color pattern is going to the upper right, And so let's change the perspective and look at it not from the perspective of space and time, but I realize the important factor is how many more space dimensions are there than time dimensions. And this is called the metric signature, the number of space dimensions minus the number of time dimensions. And so let's tilt the Clifford checkerboard on its corner. And now you can see something that really does look like a periodic table. And the significance of this is you can see that things are periodic now horizontally, but that the size of the matrices increase as you go up in higher numbers of dimensions. So in terms of the number of dimensions in the metric signature, there are 5 kinds of matrices. So instead of the usual 2 colors of a checkerboard, we have a 5-color checkerboard. And what kind of matrix there is either dyreal or real or complex or quaternionic or dyquaternionic, depending only on the metric signature. So here we've got some new kinds of numbers to describe the geometry in different numbers of spaces and times. Real numbers, complex numbers are just a real number plus an imaginary number, where the imaginary squared is -1. Dyreal numbers, on the other hand, are the sum of 2 real numbers, where L squared is +1. Quaternions are the sum of 2 imaginary numbers, I and j, where both I and j is squared to -1. And dyquaternions are the sum of 2 quaternions. So we have different kinds of numbers to describe universes with different metric signatures. As I said, the matrices that you need are periodic in S, but recursive in N. It turns out that the nature of the N volume depends only on the metric signature. That is, you square the volume, it will be positive, a positive multiple of the identity matrix for S modulo 4 equal to 0 or 1, but it's time-like for S modulo 4 to be 2 or 3. So the nature of the space-time that you're in depends very strongly, in fact, uniquely, on what the metric signature is. On the other hand, the rank of that matrix depends only on N. So starting from just 2 dimensions, and it's either the Euclidean plane or the Minkowskian plane, we can build up larger and larger spaces, 2 dimensions at a time, 1 space-like and 1 time-like. So here again is the periodic table for real geometric algebras. And again, it is periodic in metric signature. So if you go across, for example, each of these squares will step across by 2 dimensions. So you go 1, 2, 3, 4 diamonds to the right. You have exactly the same kind and size of matrix, and that's the periodicity. On the other hand, if you go up every 2 dimensions, 1 space-like and 1 time-like, the matrix itself doubles, so it's recursive in N. And this is the advantage of turning the checkerboard on its corner, because now you can see that there is a different behavior in metric signature than there is in the number of dimensions. Again, the nature of the N volume only depends on the metric signature. So we've got both the Euclidean plane and the Minkowskian plane, so let's combine the 2 of them. And the direct product of the geometric algebra of the Euclidean plane and the geometric algebra of the Minkowskian plane is, in fact, the geometric algebra of 4-dimensional Minkowskian spacetime, with the basis vectors shown there, x4, y4, z4, and t4. The geometric algebra that's created from those generated by those 4 matrices has 1 scalar, the identity matrix, doing nothing. The 4 vectors of space-time. 6 bivectors, which correspond to spin and area, 4 trivectors, momentum, energy, and 1 4-volume, which is time-like, corresponding to action. This is the real version of Hastings space-time algebra. And amazingly, the 4 momenta and the 4 vectors, position vectors, anti-commute as a consequence only of the anti-commutivity of the vectors themselves. So the geometry gives you the Heisenberg anti-commutation relations. You get quantum mechanics for free out of the geometry. Let me stop there and see if there are any questions to this point. Okay, continuing.
Yeah, let me say that you got a question. The question is if you can apply directly to quantum mechanics formalism these algebras.
Repeat the question, please, Dr. Felix.
The question is if you can't apply and obtain the results that we get normally in quantum mechanics.
Yes. Get all of quantum mechanics comes out geometrically, and that'll be one of the points that I'll expound on as we go along.
Okay, thank you.
Okay, so let's start filling in now the physics based on the periodic table of real geometric algebras. What I showed you previously was just the mathematics of different geometries of different numbers of spaces and times. But now we can fill in the physical applications. Down at the bottom, these real numbers, those describe bits, which are just numbers. Here is 1 dimension of space. Here is 1 dimension of time. And combining the two into space-time is the Minkowskian plane, and we've already described how to do that. The Euclidean plane sits over here. And remember that the Minkowskian plane and the Euclidean plane can be generated from each other. Now let's look at quantum information, because I promised you quantum mechanics for free. So a bit of information is either +1 or -1. Normally we talk of information as being 0s and 1s, but the 0s and 1s are actually labels for the bits. And if you treat the bits as +1 and -1, the multiplication will come out of the matrix multiplication itself. A qubit of information, on the other hand, is any combination of a 0 ket and a 1 ket. Here's the usual representation of the 0 ket and the 1 ket, namely the Pauli Z matrix and the Pauli X matrix. Please notice that both of them are real matrices. And also notice that those were the X carets and Y carets of the Euclidean plane that we introduced earlier. So qubits form a 2-state system. They are 2-dimensional. They are described by real 2x2 matrices. They are not 3-dimensional, which would need to be described by 2 and 2 complex matrices. So here again is the expression for a Euclidean vector. So the unit vector is qubits are unit vectors in the Euclidean plane, as I explained in the APS talk that Dr. Segura heard me speak at. And the eigenvalues of the qubits are the bits +1 and -1 for all values of theta. So qubits have rotational symmetry, so that if you rotate the coordinate system, you still have the same eigenvalues for the unit vectors in the Euclidean plane. So here we put qubits in place. They're elements in the Euclidean plane. They go here. And remember, the product of the Minkowskian plane, which is here, and the Euclidean plane, which is here, is Hastings space-time algebra. that gives you the usual expressions for relativity in 3 space dimensions and 1 time dimension. Let me say a little bit about 2x2 real matrix representations. We've already seen that 2-dimensional Euclidean vectors are described here. Notice that the x and y vectors anti-commute. Geometrically, that just means that the x and y vectors are orthogonal to each other. Complex numbers, on the other hand, are described by this matrix, which is x times the identity matrix plus y times the bivector. And notice the different placement of the minus sign. And as a consequence of that, while the x and y vectors anti-commute, the identity matrix and the bivector xy commute with one another. And so commuting complex numbers cannot describe qubits. And this was expressed very forcefully last year in a paper by Renaud and et al. But he came to the wrong conclusion, thinking that just because complex numbers cannot describe qubits, the real representation of complex numbers cannot describe qubits. Therefore, real numbers were insufficient to describe quantum mechanics. Indeed, the C vector cannot describe the problem with just the real representation of complex numbers is that they commute. And if one uses anti-commuting matrices, then the commutation relationships work out just fine. And anti-commuting complex matrices do not describe qubits. They describe Qutrits, the spin x and y and z Pauli matrices. Those are 3-dimensional. They are not 2-dimensional. So they, in fact, described Qutrits and not qubits. Indeed, one can derive the Bell correlation as the dot product between 2 qubits. But in quantum mechanics, if you go to measure a matrix, the only measurements you can make of a matrix are the eigenvalues of the matrix. And remember, the eigenvalues of qubits are +1 and -1. And so by this trig identity, you have to build up the cosine of the angle between the 2 qubits with +1s and -1s. Those are where the 2 qubits agree or disagree. This is the Bell correlation between those 2 measurements. That Bell correlation is solely a consequence of geometry. It is not a consequence of quantum mechanics. You can establish the Bell correlation independently of quantum mechanics. It has been done on logistic grounds by other authors, but here it can be done just on the basis of Euclidean geometry. So the correlation is not as surprising as the popular press would have you believe. Let's apply that to Schrödinger's cat. Here, think of a Stern-Gerlach experiment where the first Stern-Gerlach apparatus is set in the 30-degree direction so that we then block off the spin-down electrons and all of the particles that continue on to the second Stern-Gerlach apparatus are indeed at the 30-degree angle. But we measure them at the 60-degree angle. And so we're not going to get quite the same as looking again at the 30-degree angle. And because the cosine between 30 and 60 has to be built up of +1s and -1s, some of these are spin up and some of these are spin down in the 60-degree direction. So the correlation between the 60-degree direction and the 30-degree direction is exactly the Bell correlation. It's exactly what you would expect. It is the cosine of the angle between those 2 orientations. And this is most clearly seen over here at the 120-degree direction, perpendicular to the direction of the incoming, of the spin of the incoming electrons. And there, because you're measuring perpendicular, you get no correlation between the up and down in the 30-degree direction and the up and down in the 120-degree direction. And again, this is just the cosine of the angle between the two. So the cat is observed, Schrödinger's cat is observed to be in a superposition of upright and inverted, not in a superposition of alive and dead. And so I like to say that Schrödinger's cat is not a zombie. She is just being viewed cattywampus at an angle. What is perceived is a convolution of the state of the observer and the state of the observed. And that convolution is just the cosine of the angle between them, built up in terms of +1s and -1s. This geometric explanation of Bell correlation obviates the need for quantum entanglement. The correlation between quantum measurements is exactly what you expect geometrically. It is not surprising. It is not spooky, as Einstein was concerned. So spooks be gone. Let me pause there if there are additional questions.
Yes, you got one question. The question is, how can you separate geometry from quantum mechanics physics?
What I'm not separating the two. What I'm showing is that quantum mechanics physics is exactly what you would expect geometrically if the only measurements you can make are the eigenvalue, the only measurements of a matrix you can make are the eigenvalues of a matrix. I am showing that quantum mechanics, in fact, is geometry, geometry, geometry.
Thanks. Thank you.
Okay, let me continue. If you take two qubits, as one does in quantum information theory, and takes the direct product of those two, the direct product of two qubits, of the geometric algebra of two qubits, is the geometric algebra of four-dimensional null spacetime, which is isomorphic to the geometric algebra of four-dimensional Minkowskian spacetime, which has as a subspace three-dimensional Euclidean space, isomorphic to C2, that's the Pauli algebra, and that describes Qtrits. And the direct product of three qubits gives you something that is isomorphic to 2x2 matrices of quaternions, and that describes ququads. So let's take a look at where they are on this on the periodic table of geometric algebras. Here are qubits, here are Qtrits, here are ququads. Notice that all of these are Euclidean, real Euclidean spaces. They are not Hilbert spaces. You do not need quantum mechanics. You can describe them with real matrices. The direct product of four qubits, however, jumps from 4 dimensions to 8 dimensions. They give you quocs instead of quints. And so quantum information theory is found in spacetime geometries that have 0 time dimensions. These quantum information states, as I said, are Euclidean spaces over the real numbers. They are not Hilbert spaces over complex numbers. And notice that we've jumped from 4 dimensions to 8 dimensions. What happened to those intervening dimensions? So here we are, qubits, Qtrits, ququads, quocs. Let's take a look at 5 dimensions. If you take the matrix direct product of complex and the spacetime algebra, what you get is a, this is Minkowskian spacetime. This is a complex number. You have, therefore, 4-dimensional real spacetime multiplied by something with the symmetry, U1, which is the symmetry of electromagnetism. So the fifth dimension, in fact, is curled up. So one sees the geometrical explanation of why the fifth dimension needs to be curled up. But since the work of Steven Weinberg, we've realized that we need to unify electromagnetism and the weak force into the electroweak force. So here we have electromagnetism here, but we have to combine it with the electroweak force, which is U1 cross SU2 over complex numbers, but SO2 cross SO3 over the real numbers. And so that gives us another copy of four-dimensional space-time with metric signature 2, but curled up. And the direct product of those two yields an 8-dimensional Euclidean space with the 8-fold symmetry of the strong force. And so what we've done geometrically is to generate the standard model of physics up here at the 8 real dimensional level of Euclidean spaces. Spacetimes with, let me pause there if there are any questions, Professor Felix.
No, we have no questions so far.
Okay, let me continue. Okay, I've talked about combining quantum information and taking a look. So spacetimes with 0 time dimensions along the rightmost diagonal of the periodic table describe quantum information. Relativity are the spacetimes along the next to rightmost diagonal. And at an earlier APS meeting, I was asked, why is physics all clustered over on the right-hand side of the periodic table of geometric algebras? And I came to the conclusion that spacetimes with more than one time dimension cannot have a coherent chronology. Notice the root of the word chronology. It's the logic of time. And so if you try to have a universe with 2 or more time dimensions, you cannot parameterize the history of that universe in terms of one time dimension. This just has too many time dimensions. And so let's eliminate these from consideration as simply having too many time dimensions. And that leaves us with quantum mechanics here and relativity here. So placed this way in the periodic table of real geometric algebras, quantum mechanics and relativity are like the noble gases with 0 valence electrons and the alkali metals with 1 valence electron in the periodic table of chemistry. So while the highly reactive alkali metals behave very differently than the inert noble gases, they simply differ by 1 valence electron. And likewise, although relativity behaves very differently than quantum mechanics, they differ by just 1 time dimension. I like to express that by saying that quantum mechanics is space-time without the time. Now, beyond 8 dimensions, the pattern of geometric algebras repeats itself. 4 open dimensions of space-time, then 4 curled-up dimensions of the standard model. The open dimensions can grow, but the curled-up dimensions cannot. So one gets an exponentially expanding space-time lattice with the standard model at each node of the lattice. And the rate of recursion is what sets the cosmological constant. And I like to think of that. So this diagram continues on up, but the continuation is going to be of the same pattern because of the periodicity of the geometric algebras. And so that's why we get this expanding space-time lattice. And I like to think of it as a jungle gym. Here's the original jungle gym. that was constructed in 1920 by a mathematician who wanted his children to learn geometry and in particular Cartesian coordinates. And so he would tell them what, go to x equal 3 and z equal 4. And the children would scramble to find that position. So this was essentially conceived of as a mathematics teaching tool. Of course, it became wildly popular. Current gyms are a little safer than the original ones, but you can see here what I'm thinking of in terms of expanding space-time. You've got the open dimensions, 4-dimensional. At each node, you have the standard model of physics. So think of, for example, the diagram in Brian Greene's book on the fabric of space-time. The open dimensions can grow, but the closed dimensions cannot. So that's why you get this expanding 4-dimensional space-time lattice with the standard model at each node of the lattice. Now, because of recursive generation, space-time is the same from place to place. The 16th dimension looks like a bigger version of 8 dimensions, but it's got the same mathematics. So space-time is the same from place to place and from time to time. And at the nodes, the standard model of physics is the same from place to place. This tells you why space-time is homogeneous, and it tells you why physics is the same at any point across the universe. And moreover, by Nernst's theorem, the momentum energy is conserved because of the uniformity of space-time. That uniformity is a consequence of the recursive generation. So the laws of physics do not precede the universe. They are consequences of the way that the universe grows recursively. 4 open dimensions, 4 closed dimensions, 4 open dimensions, 4 closed dimensions, 4 open dimensions, 4 closed dimensions. So we're growing the universe geometrically from the bottom up. The universe, it doesn't take any, and the total energy of the universe is 0, so it doesn't take an igniter to get the universe going. It can happen spontaneously. The universe is self-beginning, not made. From the possibility of going some direction or some other direction. That gets 2 dimensions. The 2 dimensions give rise, as I've shown, to 4-dimensional quantum spacetimes. The next 4 dimensions yield the standard model of physics. And then after 8 dimensions, one gets the geometric pattern repeating itself. So you have this exponentially expanding 4-dimensional spacetime lattice with the standard model of at each node. So space itself is generous. Space itself is growing. We've known that conclusively since 1998 with the discovery of the continuing exponential growth of the universe. And we see that as time goes on, more and more dimensions, the structures that can be built are more and more complex. And so we start thinking of first chemical molecules and then more complex organisms as time goes on. Growing the universe from the bottom up has implications for the foundations of quantum mechanics, and it has the implications for the growth of structures on all scales: astrophysical, biochemical, physiological. And having just pulled through the pandemic, we can see how little complex structures can have implications on things much larger than themselves. But it's a universe that grows from the bottom up, and that has all sorts of philosophical and even, dare I say, political consequences. So let me stop there. For further reading, take a look at my paper from last year in the Advances in Applied Clifford Algebras on how to generate larger spacetimes from smaller spacetimes and how it's done. So thank you very much. I'm again open for questions and discussion.
Thank you very much. You got another question. I think you answered it, but anyway, the question is it possible to eliminate time?
Well, I think we can have universes with no time. That's what quantum mechanics describes quantum mechanics, and universes with one dimension of time, and that gives us relativity. But I think universes with multiple dimensions of time are simply do not provide for a coherent chronology.
Another question is if you can't comment of entropy.
I think we understand entropy as a consequence of the statistics of ensembles. And what this geometric method gives you is a way of constructing ensembles, larger ensembles from smaller ensembles. And so I think that will give you the standard calculations that one makes of the entropy of any ensemble. I don't think there's a change there.
Okay, thanks. I can see that Carlos Garcia is gone, and you have reached about 100 people in different networks.
Thank you.
They are very grateful with you, and so we are. Do you like to say some last words to your public, just to close your talk?
Yeah, I think the thing to emphasize is the concept of making larger spaces out of smaller spaces, and that it could be done geometrically. And so the key takeaway I would consider to be start from what's possible in 2 dimensions. And as you combine that into larger and larger dimensions, more things become possible. And what quantum mechanics tells you is not what is, but what is possible. And it doesn't determine the future. It tells you what the future possibilities are. And so what the universe looks like tomorrow depends on our exploring those possibilities today. It is not cast in stone. It is not predetermined. It is not mandated from on high. It really is the result of the actions of each of the constituents of the universe working together, and it is that collaborative creation of the future of the universe that I think gives us hope for making a better tomorrow.
Okay, thanks a lot. Thanks for your seminar, and we are very grateful. Thanks a lot.
Thank you so much.
Afternoon.
Thank you.